Thanks very much for having me to talk. I thought I would, I'm John from Godwin. I'm a senior research engineer at DeepMind, working on potentials for molecular property prediction. I thought I would have a talk about, an argument for needing things like foundation models or large, scalable, high parameter count, high flops models like we have in NLP and computer vision, and that actually we need something like that here, and that we're not too far off. I think this is perhaps a position that not many people hold in the community, so I'm expecting people to disagree with me, but I wanted to make an argument for this to stimulate a discussion. I mean, maybe, this is my first conference since before COVID, so maybe actually people already agree with me. So my argument, and I'm going to hopefully try and persuade you of this, my argument is that much recent research on molecular property prediction has focused on architectural inductive biases, things like equivariance. That's very popular. I think every week I receive a new equivariant architecture on archive, and we add physics and chemistry, feature engineering into our architectures. And this is how we improve our results, by taking our understanding about what an actual force field looks like and trying to inject some of that understanding into the network so the network doesn't have to learn it. This is in quite a lot of contrast to progress that you see in things like natural language processing, computer vision, and reinforcement learning, where the models have over time become simpler. Maybe 5-7 years ago, you'd have highly crafted LSTMs for natural language processing. You'd have a different architecture for every different task. Now everything's homogenized. So there's been a trend in other areas of machine learning, and it doesn't seem to have applied in our area. And the question I want to ask is this because our area is different, it's special, or will in 10 years' time, we'll be using one form of transformer or one form of architecture, and it looks quite simple. I think probably will have some elements of the inductive biases we're interested in, but it may look simpler than things we currently have. And the argument, the sort of final sort of observation that I would make is that the scale benefits that we've seen in natural language processing and computer vision did not necessarily come from new architectures. They're all transformers, sure, but when you have the effects of something like GPT-3, that's not just a transformer, it's the identification of a very good pre-training task and the ability to engineer that very well. And that gives the emergent effects, not just the transformer architecture. So in order to get these scale benefits, you not only need a good architecture, you also need to pay attention to what you're training and how you're training it. And so my hypothesis is that we may already have the right architectures to have something like a general purpose machine learning potential that works across the periodic table. We just haven't found a way to train it yet with large amounts of data, a good pre-training representation learning technique that unlocks the power of scale, high parameter counts, and flops. So this is what I want to try and kind of persuade you of. I'm not sure I will persuade you of, but this is kind of my thinking. So I'm going to use the phrase foundation model a little bit in this talk. And for those who don't know, a foundation model, this sort of term was coined after the introduction of GPT-3. And it's sort of termed and is kind of used to talk about things like GPT-3 and DALL-E 2 and all of these very large networks from OpenAI and folks. And the definition that I'm going to use is that a foundation model is an artificial intelligence model trained on a large quantity of unlabeled data at scale by some self-supervised learning, resulting in a model that can be adapted to a wide range of downstream tasks. So the question is, what would a foundation model look like for molecular property prediction? This is sort of my hypothesis. It's probably a simple architecture with some carefully chosen inductive biases that when trained properly can scale with the floating operations and number of parameters that you add to it and the amount of data that you provide it. So you get a nice curve that goes up. We would need a good pre-training objective. We need something that is actually going to learn a very rich and important representation of our data so that we can use it in downstream tasks. You would have strong few-shot learning on downstream tasks. So you might have your foundation model, you might get 5 points from your very expensive quantum chemistry calculation. Maybe you can train on those 5 points, and it generalizes very well, perhaps very well across the periodic table. And so finally, I think we need this to generalize very well. I think one of the sort of key observations that I had coming into this area, well, I say key observations, one of the things that people told me coming into this area was that we have very highly accurate machine learning models, but every time we want to change something about our training distribution, we want to change the elements that we're using, we need to retrain. So we don't have very general architectures. We don't have a universal force field. We have specific force fields for specific things. So now I want to take you through a little bit of the research that we've done at DeepMind to try and figure out, I think, perhaps 2 of these questions, but I think there are lots of unanswered questions here. And so the first one is whether or not we can get simple models that don't have very strong inductive biases to perform well on molecular property prediction tasks. If we pay attention, perhaps less to the physics, more to the mechanics of how a neural network works. So there's this kind of hypothesis in graph neural networks, I think in molecular property, graph neural networks, message passing networks for molecular property prediction, that they don't scale very well. And to me, this has always seemed a little bit of a strange proposition, because I don't know what the difference is between a graph attention network with multi-head attention and a transformer. And yet on the one hand, people say graph attention networks don't scale, or attention networks for molecular property prediction, but transformers do scale. This seems to me begs the question of what's the difference for when we think about scaling transformers and scaling graph neural networks. And I think it's often in the tasks that we're using. So in my sort of view, contrary to received wisdom, graph neural networks do scale very well. It's just about the graph that you're choosing. So in the cases where transformers scale very well, you often have an autoregressive language modeling graph. That's if you were to take a transformer and think about what graph it represents for language modeling, where these are the most successful things, this is the graph that it uses. And this looks very different to any sort of graph you might construct from a molecule. So that's one thing about the observation. And then the second thing is to say, well, if you choose something like this graph and then you have loads of data and you scale things up, you get these wonderful scaling laws, which have revolutionized many areas of machine learning. So the real question, I think, is not about graph neural networks, but about our tasks, things like learning energies and forces. So, the question is, for us, why are molecular graph neural networks complicated and why are they shallow? I'm using the phrase complicated here. I'm saying we're adding lots of inductive biases that you might not see in other areas. And so the hypothesis here that we had in this work was that the loss is very important. The way that you train this is very important. And so this is the kind of reason why you don't see these scaling laws that you see in transformers. You need something akin to your autoregressive language modeling loss. You want to take inspiration from that and try and find something that might give you sort of similar characteristics. So from our point of view, we sort of formulated this as this kind of problem with graph property regression, which is to say, upon initialization of a graph neural network with many layers, what happens is that you have this smoothing effect from your summation aggregations on your nodes, so that in the penultimate layers, your node latents look almost identical. And this means that if you add them up and add a linear layer to them, your gradients to your node latents are also going to look almost identical, which means that you're never going to learn a distributed, rich representation of your graph in your later layers of your graph deep network training on a graph property prediction task. So this means that there's no benefit, basically, of adding depth without something to counteract this effect. This kind of effect is called oversmoothing in the literature. It's a little bit like diffusion. So on the right-hand side, you can see a kind of a GIF of what diffusion looks like. So this is what kind of your node latents look in a graph neural network upon initialization. Is you start being very distinct and having this structure. And then as the diffusion process goes on in time, or as you add layers, it will become identical. And this is a sort of catastrophic effect for graph neural networks, and that's why you don't see depth. So our sort of question is, how do you benefit from scale? Because we know that depth is very important for anything other than graph neural networks, it seems like. So one One sort of part of the dilemma is that you can go sort of shallow and not over smooth. And I think that's the way that we've currently gone. And if you do that, then you can't get the benefits of depth and high parameter count. And so you have to add in your feature engineering, you have to add in your inductive biases to get the network to learn. And on the other hand, you have this deep over smooth problem where your gradients, your nodes are very similar. And so you never learn anything anyway. And this is the problem that we're in. And I think most of the time we've taken the right-hand path in this dilemma. But I would say that there's an alternative, and it's kind of embarrassingly simple. I think so simple that people say it's a little bit of a trick. And maybe it is a little bit of a trick, but it works quite well, which is to say, well, you probably don't get this over smoothing, or you don't get identical node gradients if each node has a loss and each of those losses has a different value. And the way that you can construct that is by constructing an arbitrary auxiliary task, which is to add some noise to your nodes and then have a denoising loss on your nodes. And this gives you a different gradient for each of your nodes. And this also has some nice interpretation. It's learning, you know, this is basically a denoising autoencoder. You can think of it that way. A denoising autoencoder, for our case, working on 3D molecular graphs, this is learning a mapping from high energy to low energy states. And so it has a kind of representation learning quality, which is well known in the machine learning literature too. So on the right-hand side, you can see the effect of adding something like noise and nodes. And this is a kind of measure of similarity of our node latents. And you can see basically on the left-hand side that sort of dissimilarity, independence of the node latent features is maintained all the way through the network. And this means that we take this very simple graph neural network that was originally designed for fluid simulations and has very few inductive biases. It has translational invariance. I think that's the main one that you can think of, and locality, but I guess every message passing network does. It's called GraphNet Simulator. I should add the reference. We add this noise and nodes loss, we see increased benefits with depth, which is something we don't normally see. And we see that this very kind of simple network with very few inductive biases beats the previous state of the art on this Open Catalyst benchmark for predicting energies of ground state DFT relaxations from a catalyst and absorbent pair. So this seems to work quite well. So this is kind of, for us, this has kind of proved our hypothesis that maybe, maybe we do need better architectures than GNS. I think we almost certainly do. So it's not an argument for using the most simple architecture. It's an argument for saying we're leaving things on the table by not paying attention to the mechanics of machine learning, as well as our understanding of physics and chemistry and putting them in. So that's one paper. The second part that I want to argue for is that we should think about pre-training a lot more, because pre-training was the thing, I think, from natural language processing that opened up these very large language models and made major breakthroughs. I have friends in NLP now who say, well, I should just give up. I shouldn't finish my PhD. I should go do something else because there's literally nothing I can do in my university department. All the tasks that I had thought of, they're being solved. There's been a dramatic transformation in that area. And it's really pre-training that's provided that, GPT, generalized pre-training. So this is an archive paper that we've recently put up, and I'm going to walk you through this. What would pre-training look like for molecular property prediction? And we make the argument that learning pre-training would be to learn a very good, learn a force field. Ideally, it sounds a little bit strange, but really what you'd want to do is you want to take a lot of high energy states, evaluate the forces, and train a model to predict the forces in the forward path, so you get this distinct per node loss. So you can have a big network and you can get the thing that we said in the previous slides, and then you learn a very good representation of your energy landscape. That would be ideal. But of course, we can't do that because it's quite difficult to evaluate forces. So our proposed solution is to use a sort of pseudo force field, where we can guarantee that the force field has the same energy minima as the true force field, but it's very easy to sample. And then we'll sample a load of states all around our energy landscape to learn a very good representation, a very dense representation of our input space. And we can basically synthesize unlimited data this way. And I think we probably could use a traditional force field as well. So the observation that we make is that denoising is the same thing as learning a force field defined by a mixture of Gaussian's distribution. So you can just add noise to your inputs according to some noise schedule, predict the denoising object, predict the noise that's been added, and you can add noise sort of schedule so that you get into very high energy parts of your input space, and you can also add noise to get in the very low, like local minimum input space, so you can get very good coverage. But simply this denoising objective, which is simply the squared loss, is the same thing as learning this force field defined by these mixture of Gaussians. So the way that we do this is we just add noise and we just denoise. It sounds very simple, but it works very well. So here we have, again, we've kind of used GNS-TAT, and on the next slides, we have some results from TorchMDNet to convince you that it's not GNS that just works this way. But this is a result on QM9, the test HOMO MAE. And here, so of course we use more data, so it's not necessarily the best comparison, but to show the impact. We pre-train on this data set called PCQM4MV2. It's about 3 million DFT ground structures of small ground molecules. There is a little bit of overlap between QM9 and PCQM4MV2. You can have a little look in our archive paper to see this. We pre-train with this denoising objective, so we don't know nothing about HOMO. And then using this pre-trained network, we managed to get down to almost 40 MAE. And this is, I think, similar to the gap between the top 4 previous state-of-the-art results on QM9. This is a big jump. And it also works for TorchMDNet, which is, I think, a paper that was put out by the organizers of this conference, where you can see, you can add noise. So this hypothesis about noisy nodes and adding noise to improve the depth of networks applies to TorchMDNet. So it's not something that's just designed for simple architectures. And then pre-training also works well. So you can take your favorite architecture with your inductive biases and your covariance, and you can hopefully scale them up using these techniques. So hopefully this has convinced you that pre-training and paying attention to the mechanics of networks are important things to be thinking about for the future. So I'm going to make a few predictions for the future about what I think will happen in this area. And these are my predictions. These aren't the predictions of DeepMind. I'm sure you can find people at DeepMind. It's a big place to disagree with me. But I think what we'll find is that the architectures in 5–10 years' time, they're going to be simpler than the ones we currently use. I think we'll reach a point where we've added quite significant inductive biases and feature engineering, and then we'll find that things are better as we simplify. And this is kind of, I think, what we've seen in other areas of machine learning. This isn't to say that there will be no inductive biases. I think particularly equivariance will end up being important in some way, or invariance. It's going to be important in some ways, but I think these are going to be simply defined. I think perhaps we already have the techniques that are present in a lot of papers to do this. I think the simpler, the better here. I think a really sort of universal force field, general purpose machine learning model that works on lots and lots and lots of things will probably have many more floating point operations. I know this means that perhaps other, like problems like molecular dynamics, where you need very, very fast inference time, this may not be as suitable. But I think to get the highest performance, we'll be able to add flops and see higher performance going up. And I don't think that necessarily means many more parameters. I think we've already seen this. So I think that the one thing I would like to see more in papers, especially around papers that use spherical harmonics, is analysis of the floating point operations. Because papers with these tensor products have huge amounts of compute, but very few parameters. So you're kind of fudging things if you say, oh, I've only got 1 million parameters, but actually the floating point operations are the size of a large transformer, which is actually the case. We'll have methods for representation learning, and we may need very big models. We may need things like model parallelism. I don't know. But these are predictions. I'd like to be able to chat with people about these over the coming few days. First time, I think, that I have presented this. So I'm expecting to change my mind, or maybe change your mind. We'll see. Thanks very much.
Thank you very much, Jonathan. I think we're going to have not enough time for Q&A because this was excellent, and I'm sure people will have lots of thoughts. So let's do one quick question before we jump off to the next.
Yeah, so my question is regarding this problem do you feel like techniques like working notes can improve the quality of the signal maps?
Yeah, I think that's a good question. I think so. I would believe so. I think maybe perhaps the way I would phrase it is slightly different, which is that I think that the richness of your representations is going to improve really significantly through using things like this, and that's going to give you a better model. And then it's going to give you more interesting explanations. You know, my sense may be that you don't get really great explanations from highly feature engineered inductive bias based models because a lot of the explanation is already baked into your network. You don't need much explanation there. So I think the answer is yes in a roundabout way.
Thank you. I misinterpreted Gianni's hand signs. We do have a 1 hour coffee break, so we can trade some time from the later coffee break to now and continue the conversation. I think there were plenty of interesting things said about scaling and flops and spherical harmonics. I don't know if anybody in the audience had thoughts about spherical harmonics. Any?
No spherical harmonics. But I would like to come back to your point about so you mentioned the language models, right? But these have, GPT-3 has 175 billion parameters, if I remember right. Mm-hmm. So you also mentioned generalization across chemical compound space. So that also sounds like a lot of parameters, right? But the whole point of this is to replace the physical methods, right? And if you have that many parameters, how can you still be faster?
Mm-hmm. Yeah, so I think that's a very good question. I think we still have an open. So GPT-2, which I think was also a breakthrough, had very, very, very many less parameters than GPT-3. So I think we're going to be able to see, and you know, I think like some of these models, like this, like TorchMDNet has very few parameters as well, but you start to see benefits from pre-training. So I think there's going to be a trade-off. You probably see a curve, and you probably look at your inference time, and you put a point and say, okay, here's the inference time. But I think you're still going to be seeing benefits from things like pre-training simpler models. And actually, I think the most recent research on language models to say that if you have the right task and you actually need probably fewer parameters than GPT-3. GPT-3 was undertrained. You can get the same performance of GPT-3 with fewer parameters. So, but I agree. I think there's an important point here, which is that this isn't the same area as these kind of large language models. Inference time is a lot more important here, and so you may not be able to have the same number of parameters of floating point operations. But I would really like us to spend more time almost on exactly the points that you made, because I think that we mistake parameter counts for inference time. And actually, the truth is a lot more complicated than that. The truth is that some of the operations, you know, you can reduce your parameter count and reduce your floating point operations by using a sparse neural network, but a sparse neural network isn't going to run as fast on GPU hardware, so you're actually going to get a longer wall clock time. So sometimes I feel like this efficiency argument isn't properly pushed in the literature in the way that really satisfies me, which is using parameter count as a proxy for the real thing that we care about, which is wall clock time and implementation efficiency.
One from Alex here in the front.
Maybe just a follow-up, little bit provocative question. Don't you think that, you know, training these models, so you train at a week for 1,000 A100s, right? So a lot of chemistry problems can be solved directly, given that amount of compute. It sort of defeats the purpose.
I would perhaps disagree with some of that. So, you know, we run a lot of DFT calculations. I know a lot of people will run a lot of DFT calculations. And sometimes I wait a week for things to, use a lot of Google CPUs, and I wait a week for things to happen, especially for these kind of relaxations. If I use one of my models, which has 200 million, it's trained for, it's not quite the sort of amount of time that you're speaking about, but I've used one of my models which has maybe hundreds of millions of parameters. It's quite a big model in comparison here. I can do the same number of relaxations in 3 or 4 hours, or sorry, I say 3 or 4 hours, like in like a day, and I can continue to do these things. So I think there are certain classes of, DFT is big science, and I think that if we get to something which, training a model for a week on 100 A100s, and then we use it for 3 years to do all of our DFT, I think that's a good trade-off. I think that's the sort of thing that I'm thinking about. I think you amortize that compute cost over time. I think that's almost what we're seeing again in some of these areas where you actually, you train one of these models once a year and then you use it for all sorts of other things. I don't know if that answers your question.
I have a couple more back there.
Thanks. Well, first of all, thanks for the talk. You made that point that we've seen all these scale benefits in natural language processing models, and in molecular property prediction, if you're not trying to predict DFT calculated values but experimental ones, you have no chance of ever getting that amount of training data to, sort of satisfy all the parameters you might have in a larger model. So do you think this whole point that you're making, that those scaling laws would be nice, really only applies to synthetic data?
Yes, this is a good point, and I think this is so the really striking thing to me about these sort of, I'm going to use the phrase foundation models rather than GPT-3 because I think it applies to different things, is that these things are few shot learners, which means that you give, once you have got your very good representation, which is kind of close to what you actually want to use it on a downstream task for, you give it a few examples and it generalizes very well. I don't have evidence for this, but my hope would be that you've learned such good representations of, your input space, your synthetic energies, that it becomes easy to generalize when you train it with experimental data. So you're not training from scratch, you don't have a billion parameters, you already have a very rich representation of your inputs. I don't have evidence for this, but this is, I think, a missing point in my slides and something that would be great to be able to see. It's been the case in other areas, maybe it's not the case here. But I think another way of putting it is, I see this as an alternative to handcraft feature engineering. What you're doing is learning features. These are, if you take the inspiration of other areas of machine learning, these are often very rich, very flexible features that are better than handcrafted features. And these features allow you, these are the replacement for inductive biases that allow you to learn very, very well. And so I would see this as having the same effect as feature engineering for your existing networks, the effect being for feature engineering and inductive biases that you learn from small amounts of data, you're very data efficient. So my expectation is that it would be the same here, but this is an outstanding question that I don't actually have an answer for.
Thank you.
All right, thanks for the great talk. I really enjoyed it. You've discussed scaling in terms of parameters. Okay, maybe also discuss some terms the scaling into the number of nodes and atoms. Do you think these large transformer models would scale well in that regard?
Yeah, that's a good question. So it's something that we've actually worked on. So you certainly can scale these things up quite nicely. So I think there are kind of two methods. I think there's one which is to say, okay, I'm not going to take into account long-term interactions. I'm just going to do some like hard cutoff, which I think is an approach that's been suggested in recent papers. So that's quite straightforward. You just like take your, slice up your input space and put one bit onto one bit GPU, one bit onto another GPU. But certainly we can take, I think what we can do, because the message passing framework, I think, is very similar to molecular dynamics simulations in terms of its computation, in terms of the way you think about optimizing it. I think we can take a lot of inspiration from molecular dynamics simulations to scale this on for multi-nodes. We have a little bit of work actually in our Giraffe JAX library on scaling graph neural networks to tens of thousands, not hundreds of thousands of nodes.
Thanks.
Okay, thanks very much, Jonathan. It wasn't as controversial, I think, as you know, people are very polite. So thanks very much, and we'll move on to the next speaker now.